Ini kita bertiga, Willy sama Mita. Yang ke ini. Oh, iya ini Willy. Oh enggak, belum di follow kan? Enggak, kemarin gua lihat masih ada. Mas jangan dia langsung ganti akun. Berapa sih? 3. Ayo lo, ayo. Bukan ayo. Oh ya ada nih. Ada. Ini manufacturing proses. Oh. Ada. Kan itu kan. Ini satu lagi ke atas sama bawah. Makanya minta dulu. Wah, ada aku ada. Ayo guys. Coba. Ada.
One mode.
Berarti bisa ikut lagi. Oh yes, dia udah ada. Ini apaan ya?
Okay, my laptop is restarting, so I'm just gonna try doing the attendance on that thing, on the link I gave you in the WhatsApp.
Bisa nggak sih buka dari sini aja terus ya kita semua scan.
Does it work? Does it work?
Oh.
Okay, anyone who hasn't done so. Okay, everyone good?
Yes.
Anyone not doing this yet? Okay, those of you in the back, you wanna move up. Today we're doing more whiteboard stuff. So we're doing more calculation stuff today. Yeah. Okay, you're gonna have to WhatsApp me because I closed the door. Oh. Didn't be attendance? Didn't be attendance? Okay. Find the link in the WhatsApp group if that still works. I don't know if it still works. Once I save it. Yeah. Okay, so let's review a little bit from last week. What is a shaft and why is it relevant to this course? What is a shaft? Okay, you want to transmit power. A shaft is the means to, transmit power useful to useful work, right? Because most engines, electric power motors, they spin things, right? They spin things. It's just practical. So a shaft is basically the power takeoff, so-called power takeoff. I borrowed that term from tractors. Tractor. The difference between tractor and a car is that a tractor has a shaft in the back to take power from. So, like if this is a tractor, there is always something behind it, right? You're pulling a harvester to plow and etc. And so where does all that mechanism in the back, the power comes from? There is a shaft at the back of the tractor. So a shaft is just, that's where the power is. That's where your motion is. And then you can do whatever you want with it, right? You can do mixing, you can do grinding, you can do milling, machining, anything, right? And so you need that shaft. And then we mount things on the shaft to manipulate gear ratios or coupling, everything, right? So today we're talking about the shaft design. Okay, so how do you design shaft and what are the design calculations involved to do that? So if you look at the shaft, I'm trying to find the figure. Okay, So if you remember what we talked about when you have a rotating shaft. Okay, when you have a rotating shaft, and of course the shaft is rotating, otherwise it's not useful. Otherwise it's just a rod. So when you bend, when you have loading on a shaft, and then you rotate it. So let's say you have a load like this, you have always the bearing support. How many bearings? Two bearings, right? So this thing is rotating, right? Rotating. And so this is going to create a bending like that. But if you imagine yourself as being part of the shaft, as it rotates, then you are going from a compression on the top, and when you're on the bottom, it's tension. So this is compression, and this is tension on the bottom. In fact, if I cut through this, if I make a cut like this, and then do the beam analysis, actually let me keep this side. Okay, so let's say you have two forces like this. And then I make a cut in the middle. This is the cut. Okay? These are the loads. What is inside this cut? Do you remember? Internal stresses. Come on, guys. It's only been a year.
Shear force.
Shear. Okay? So you got V, and you have what?
Moment.
Moment, right? Internal moment. So if this is F1, F2, you have V, and you have internal moment. Now, if I zoom on this a little bit, this internal moment actually create a normal stress distribution along the width of this beam. Okay? What is the distribution like? If I bend this thing, okay, what's going to happen on the top? When it breaks, when I bend it and then and then it breaks, what happens at the top? It tears which way? Out, right? So the top breaks out, and the bottom just kind of maybe a little bit buckling here and there, right? It's going to buckle. So on the top, the tension is going out like this. On the bottom, it is this way, right? If I cut here. So on the top, it's out of the surface. On the bottom is into the surface. What about the middle? Recall? Neutral axis. Remember neutral axis? All right. This is a neutral axis. And what is the definition of a neutral axis? Huh? It's a point where the stress is zero. Okay, we're getting somewhere. So it's zero here, it's maximum tension here, and it's maximum compression here. And the distribution somewhere in the middle is, it's zero here, so it is decreasing like that. Those of you visual people, does that start to bring back some memory? Good memory, bad memory? Okay, so bending, when you bend something and then I cut a section in the middle, you're actually seeing this. And that's why, again, I always want to bring the practical side of it. You see that here in this area, it's not doing much. Not as much as the top and the bottom, right? And that's why we often make this hollow. And so this is why you often see a beam with a hollow, right? And construction, constructing all these, oftentimes is hollow. Or maybe you have I-beams. Right? You have beams like this, with a cross-section like this. Why? Because the middle is not doing much. So I get rid of the mass. Why would I make it a solid block? Because the middle is not doing much. I cut it out. I cut it out. And so what I end up with is an I-beam. And that's why you see this in constructions. Because with bending, what is important is the top and the bottom. Okay? So, going back to shaft. Because of this, you see, if you're here, you are in tension. If you're here, you're in compression. And the difference now, different than I-beams in constructions or buildings, this thing rotates. And so you're going from compression, actually, not directly to tension, you are actually gradually decreasing. So, if you're sitting here, and then you go to the behind, right? So if this shaft is round, by the way. This shaft is round. So if I draw it from this side, okay, it's rotating. So first, here it's maximum tension. And then I rotate, and a millisecond later, I'm here, right? This is me here. And then I move. Another millisecond later, I'm here, and then I'm here, and then I'm here. And this is maximum compression. So, what happens to me, the stress I'm experiencing, I'm going from maximum tension to maximum compression, but I'm going through it, I'm not like maximum tension, maximum compression, right? I'm not like positive 10 to negative 10. I'm gradually experiencing that fluctuation. And so what is happening? It's called a cyclic stress. Okay? Cyclic stress means it's cycle, right? It's cycling. And because the shaft is rotating fast, remember? Think about it. An engine rotating at 600 RPM. How many revolutions per second is that? 600 RPM means 600 revolutions per minute. You divide or you multiply. Revolution per minute to revolution per second. Do you multiply by 60 or do you divide by 60? Who said multiply? Okay. You divide, right? So this is 10 revolutions per second. And that's pretty fast. I mean, like, and so you're experiencing this fluctuation 10 times per second. Like, right? It's pretty cyclic, very much fluctuating. And this is at idle, by the way. 600 RPM is close to your idle speed. And imagine what happens with 6,000 RPM. So it's 100 revolutions per second. And so you are experiencing maximum tension to maximum compression 100 times per second. So this is what causes shaft failure. So what causes shaft failure is not a static loading. This is called a dynamic loading, right? It's a dynamic loading. Remember the analogy I told you about paper clips? You know, we often play with it. You're listening to a lecture, you're bored, and then you start bending it. First few bends, it doesn't break, and then suddenly, right? Even if you bend it a little bit. So that's dynamic. stress or dynamic failure, not static failure. And what happens is that this fluctuation creates micro cracks. It creates micro cracks on the shaft, and the crack starts to be cycled and propagate. So this loading, okay, produces stress that are variable, repeated, alternating, or fluctuating. Of course, what I gave you is bending. However, there are also cyclic stresses that are not bending. There are torsional cyclic stress. Anyone have a ballpoint with that thing? Never mind, it's too small to show you. Anyway, so the spring, right? So when I compress this spring, a spring is actually made from a wire, right? If I open it up, it's basically a wire. So when I compress the spring, what am I doing to the wire? Am I bending it? Twisting it or axial? You're actually twisting the wire. We'll talk about springs later on. But anyways, when you cycle a spring like this, you're not cycling like this on the wire. If I open it up as a wire, you're not doing that. You are doing that. So a spring under dynamic loading, you're actually doing this. So it's actually torsional cyclic stress. Connecting rods in the engine, the piston go up and down, right? It's under axial cyclic stress, which is, axial is always not a big problem, but hey, if it's a big load, it can crack also. So basically, you are doing compression, tension, compression, tension. Okay? So that's axial cyclic stress. So we are talking about cyclic stresses, and we're talking about maximum stresses well below yield strength. So remember, what is yield? Tell me, what is yield? What is yield strength or yield failure? Fail. So the definition of yield failure is, when we say fail, you're talking about deformation. Okay, so you're deforming an object and it doesn't return to the original shape. And that's what deformation yield failure is. You're deforming it, you're bending it, and it doesn't come back. Now, if a material has a yield stress of 600 megapascal, then what we're saying is that with dynamic or cyclic load of 200 megapascal, you can actually fail or yield the material. Interesting. So you don't have to get to the yield strength in order to deform the material permanently. You can actually fail the shaft well below that. And this occurs after many stress cycles. So we're talking about thousands, tens of thousands, or even a million cycles. So we're not talking about something that breaks immediately. It breaks over a lifetime. And this becomes a problem with engineers, for engineers, right? Why is it a problem? If something fails, not on the first cycle, not the first time you use it, but after, say, 150,000 cycles, what kind of challenge does that give to you as an engineer? Cost? No, it's not cost. Like, you're designing a product to me, right? For me, like say it's bottom, and then it's gonna fail after 150,000 opening and closing. And to make the matters worse, you cannot predict this with precision. I mean, it becomes a warranty issue, right? How long will this product last? And to make things worse, this is something that is hard to predict. It is hard to predict. We're dealing with statistics here. Like, if I say, okay, the yield stress is 600 megapascal, I'm loading it at 200. What's my lifetime? We can predict it with, I don't know, 90% accuracy, but not exactly. So that's the hardest. And then, when it fails, it's going to fail by ultimate fracture. It's going to be like, break. Because it's a cracking type of failure. It's not like it's deforming. Like, remember we talked about yield, okay? Deformation, you bend it and it doesn't come back. But it's still attached. Dynamic or cyclic failure, because of these many stress cycles, it actually fails suddenly. So it breaks. So it becomes catastrophic in nature, right? And there is no visible warning. Because when you cycle this, there is a crack. You cannot see it. It's only microscopic. So there is no way we know right before it fails. Suddenly, at 150,000 cycles, it just happens. So this is the challenge with shaft design, and we're going to get into the calculation of it. Okay, and I will spare you from the derivation of the formula. Okay? When I took this course, my professor go through the derivation. I was like, who cares? We'll just use the formula, right? So yeah, you're welcome. We're dealing with bending and torsion, right? Bending and torsion, and I will not discuss the formula because I'll just show it with a problem when we're doing the calculation problem. Okay? So let me highlight one more thing about shaft and failure. We talk about the bending and the failure mode, but the question is, where will it fail? By the way, you know why we have these different diameters? Who can tell me why we have these different diameters? Yeah, hint, look up there. So you want to fit elements onto the shaft. Gears, pulleys, belts, sprockets, okay? Because we want to put things on it, and it needs to be axially positioned. The easiest way, just make a step like this. And besides, if you make it straight, it's going to be weakest in the middle. So oftentimes you make it bigger in the middle, but it also is for positioning bearings, gears, etc. And so you push it until it stops. Okay? And that's the location for the gear. Now, because of this step, you have what is called a stress concentration. Okay? Say it with me so you remember. Stress concentration. This is where the stress is concentrated. So, every time you have a sharp corner, so let's say this is the shaft I'm dealing with, okay? Say for a fan or whatever. This is a stress concentration. And I don't know whether you know this, but whenever you have sharp corners, it usually breaks there. Hmm? So if I bend this, this is the failure point. Or this. Not this, because, I mean, you're not, I mean, it's actually low stress point. So, you do what is called a finite element analysis. This is called the stress flow lines. Okay, so these flow lines, and it's actually an analogy of like a hose. If you stream water through a hose, and then there is the sudden change in diameter, the water is forced into it, right? And so these flow lines is kind of the analogy of stress concentration. So if I have a shaft like this, and I load it with bending, you see the red color, that's the maximum stresses. Okay? So that's the location of the failure point. So it's not going to fail here because the stress at this point will be multiple times the stresses everywhere else. So even though this is a small diameter, you will think, hey, this is weaker than that. So you will say, okay, it's going to break here. Yes, if this is not there. But because of this sharp corner, this is experiencing 3 to 4 times the stress. That's the kind of multiplication factor we're talking about. Not 10%, not 15%, but 200%, 300%. So that's why I'm not worried about this, and I'm not worried about this. In every shaft analysis that we're going to do, we're going to deal with the critical points only. So, yes, the diameter of the shaft is not that big of a deal. The radius is. So, for dynamic loading, stress concentration effects must be applied. In fact, this is going to be the focus of the calculation. Now, this is a simulation, again, finite element analysis, where you do computer simulation, basically, with different radiuses. Okay, this is, the radius is 2, 1.7, and 1.35. And you will see that, it's not as obvious here, but the smaller diameter or the sharper the corner, you guessed it, the greater the stress concentration factor. So this is what we're calculating. Stress concentration factor. So the stress concentration factor is called Kg. And this is the magic number. It basically says if the stress concentration is 2, basically the stress, the maximum stress at this point is 2 times the stress around it. Simple as that. Okay, this is 2 times what it would be if there is no effect from this radius. And so, if you have a generous radius like that, say 5 millimeters, this is 1 millimeter, and this is like 0.2 millimeters, right? So the more generous the radius, the better it is, meaning lower stress concentration factor. This close to sharp is the worst, and you will see it in the calculation. Okay? There is also the effect of what is called a notch sensitivity. The notch sensitivity is how sensitive is the stress concentration effect to notches. No material is perfect, just like all of us. No one's perfect, and that's an advice for dating, by the way. But every crack will introduce risk, right? This cycling will begin at any defect it has, and so any crack will be more sensitive, and so we have this as part of the calculation too. All right? So what we will do is basically we will use charts, because again, this is not, okay, this is the difference between science and engineering. Science deals with exact stuff. Scientists deal with like 2 plus 3 equals 5. Not 5.01, not 5, not 4.9, it's 5.0. We engineers, yeah, it's approximately 5. Okay? 5.1, 4.9, it's okay. It's around 5. Okay? That's the difference between scientists and engineers. We engineers, we approximate. You know, a good engineer, I think, can hold this in their hand and say, that's 100 grams. Great engineer have a good intuition to estimate something, technically, obviously. So, these lines, how is it generated? Lots of experiments. Lots of experiments. The dots kind of scatter, and then you just say, yeah, let's make an approximation. And so this chart is the guidance then to determine stress concentration factor. So this chart is basically, we will use this. This is radius divided by diameter, and this is the KT. And so this is my diameter difference, d over d. This is the radius divided by the small diameter. Okay, 0.15. Okay, it's 1.6. The KT is 1.6-ish. Okay, just an approximation. So we look up charts like this to determine KT. And this is another chart. This is for the notch sensitivity, Q. And again, it'll be more obvious once we use it. So when you have a situation like this, okay, I want to try to connect this to what you guys, because this course is actually a continuation of strength of materials. In strength of materials, this is what you do, right? If you remember, maybe, okay? Sum of moment is going to be moment, this moment, and then force times distance, clockwise, counterclockwise, F1 times distance, positive or negative, depending on the power. And then you solve for M. Now this M will be the bending moment that will create the failure here. So when you're presented a problem like this, you are basically interested to determine the internal moment, not here, not here, not interested in that, because I know it's going to fail either here, or here, or here, or here. Those are my candidate failure points. And so I will be interested in the moments M at these points only, A, B, C, D. Okay, not interested here. Only at the stress concentration factor. And basically, after doing this, you will draw shear and moment diagram. Favorite topics, right? I know. So it's 0 here. It's maximum somewhere here where that force is. But again, I'm not, even though this is maximum moment, and I can bet you on this, this is not going to be the point of failure. Because MB at this point, or MC at this point, is going to be multiplied 1.7, 2.0, 2.5, okay? So the effect from MC, even though the moment is less than M max, is going to be multiplied 2 times, 3 times over, which will result in greater effect than M max, even though M max looks like it's greater. Okay, so we're going to do the calculation. Oh, let me just mention this. Stress concentrations are due to bearing mountings, right? And so there are techniques where you can kind of enlarge the radius to reduce the amount of stress concentration. Okay, so let's kick it off with this one. Nope. example 7-1. It's a bit warm, don't you think? Dixie, it's not warm.
Like the one you put last time. Last time you put outline. No, you
Okay, by the way, this is called a shoulder. This is a shaft shoulder. So let's read the problem. And I encourage you to actually write this down. Okay, you learn more while you're writing. So take out a piece of paper or tablet. At the machine shaft shoulder, the small diameter D is 28, the large diameter D is 42 millimeters, and the fillet radius is 2.8. So let's say this is a shaft. This is the big diameter. This is the small diameter, D. Small d, big D. So small is 28, big D is 42, and the fillet radius, this R, is 2.8. Okay, so go ahead and draw this so you can visualize it. I know it doesn't give you a visual here. So this is machine, right, on a lathe. And this is the radius. Now, they calculate the bending moment at this point. M is 142.4 Newton meter, and the torsion T is 124.2 Newton meter. And some of the concepts I will explain to you as we go along, because otherwise you'll be overwhelmed with all these concepts. I want to explain it with an example. And we're given the ultimate strength, SUT 735 and SE 205. And I'll explain to you what these are. Okay? So we want to know the fatigue factor of safety of the design using the fatigue failure criteria. By the way, fatigue is the failure mode of cyclic. Okay? The cyclic failure is called fatigue failure. Fatigue as in lelah, right? Tired. Because like you're cycling it and it becomes tired. So that's the term they use, fatigue. Okay, using a fatigue failure criteria described in this section. So fatigue failure is contrasted with static failure. Okay, static means you load it once, boom, it cracks. Fatigue, you load it many times over 1 year and then suddenly it crashes. Okay, so fatigue versus static failure. You know, in the textbook, we discussed this in chapter 1, but I skipped that. I'm a practical guy, so I teach by example. So once we get into the example, I'll explain to you what these are. Okay? So, let's proceed. Before that, I will have to explain to you the concept of endurance limit. So, let's talk about SE for a moment here. You know what the ultimate strength is? What is the difference between ultimate strength and yield strength?
Oh, before it breaks off completely.
Yield strength is the stress at which you cannot return to your original shape, right? What about ultimate strength? Ultimate strength is when it actually breaks. Okay? You pull it, specimen for testing, you pull it, and then it starts to neck, that's yield. Okay? And then when it breaks, that's ultimate stress. So we're told that this material has an ultimate strength of 735, and I explained to you before, it can fail well under that, right? And I usually have one lecture just explaining endurance strength. We're skipping that because I think it's just less practical. But I have to explain to you the SN diagram. Okay? The stress to number of cycle. So N is number of cycle, S is the strength. Okay? Now, we begin with SUT here because at 0 cycle, if it breaks at 0 cycle, like the first time you load it, then your strength is basically ultimate strength. But you are actually going to see this curve. So basically, if I load it 100 times, 1,000 times, then it's gonna fail. This 735, it's gonna fail at like 600 or 400, let's say. Okay, but then there is a point. You see the line? What does this mean? This line. Like if I load it 400, its lifetime is 1,000. If I load it 550, its lifetime is 100. This is 10,000. This is 100,000. This is 1 million. This is 5 million. This is 10 million. What does that flat line tell us? Come on. Try to imagine. This is 205. This is called SE. This line. This point. 205 megapascal. And this line flattens at SE. Let me ask you this. If I say, if I have a fluctuating load of 550, it fails at 100. If I give a cyclic load of 400, it fails after 1,000 cycle. What happens if I load it 100 MVA? It will never fail. That's right. So SE, this is called the endurance limit. The endurance limit is the stress below which your shaft will have infinite life. So as it turns out, you know, the paperclip we bend, if you bend it so light, very light, you will never fail it. It can go infinite life. So this is a very important number, don't you think? So 205 MPa is the magic number. If I make sure that my shaft is stressed below 205, then my shaft will have infinite life. No fatigue failure. Now, we still need to analyze the shaft. And the question asks us, so, you know, with this design, what is the factor of safety so that I don't fail, right? How close am I to failure? Because 205 is the magic number. I want to be below it. But as it turns out, how far I am below that is also subject to some calculations, which we will do. Okay? But SE is 205, that's what that means. And I'll have to give you that number. Okay, so let's begin the calculation. Now notice that we have a bending moment and we have a torsion. I want to again remind you bending moment and torsion, steady torsion. Why does it say steady? Well, that means my torsion is not cyclic. What is cyclic here is bending. So when we want to calculate the stress calculation factor, we have to consider torsion and bending separately. Okay? So there is the bending and there is the torsion. The bending is cyclic. The torsion is constant or steady or static. And this is often the case. And you will be given formulas that contain both, but you can actually stretch out many of it. So this formula becomes simplified because the alternating torque and the mean moment they are zero, because only the bending creates cyclic loading, but the torsion does not. Okay? So that's why I need to talk about that. Now, so what is the stress concentration factor? So we go here. Of course, you'll be given this figure during exams. So we have a cyclic or alternating moment, MA. And MA is 142.4 Newton meter. MM is 0. So this is the mean moment, because this moment is cyclic. Remember? Talked about that enough, I think. So here, the torsion, the alternating torsion is 0, but the mean torsion is 124.3 Newton meter. Okay, so this is the alternating, this is the mean. Now let's talk about the stress concentration. Here is a chart for the bending moment. There are two kinds of chart. They look similar. Be careful. Look at this. This is M and this is T. Torsion. Okay? Be careful. I will always give you two charts. So now in order to use this chart, I need two numbers. I need R over D and I need D over D. And I have to do that calculation here. So D over D is 42 divided by 28, 1.5. R over small d is 2.8 divided by 28, 0.1. Okay? So these are the two numbers you need to do in order to use the chart. So here's the chart. R over D is 0.1. You go up and you find the line that is closest to the d over d that you want. This line is d over d equals 3. This line is d over d equals 1.5, 1.1, 1.05, and 1.02. Now what if yours is 1.07? Yeah, it's somewhere there. Okay, just kind of estimate. So thankfully we are here, 1.5. So d over d is, this is the line we use. It's red. Okay. This is the line I'm interested in. 0.1 R over D, 1.5 D over D. Any questions? Okay. So that's the intersection. This is my KT. Or KF, sorry. This is KF. I'll show you why it's KF later. Okay, so that number we estimate. Keep messing this up. Sorry, this is KT. KT. It's correct. KT. KT is 1.68. Yes, that's from the textbook. I don't have that good of an estimate. Yeah, I would say that's like 1.7 if it were me. But this is from a textbook example, so 1.68. Questions? Okay, the next thing we look up is this chart. This is called the notch radius. Okay, that in a way. The notch radius you look up by R on the top, the radius, and these lines are the SUT. Our SUT is 735. Our radius is 2.8. So, this is R equals 2.8. Missed that bit. Alright, I'll follow my own slide. That's R equals 2.8. And then this guy, 0.7 GPa, gigapascal. My SUT is 0.73 gigapascal. I would say this is the line we're interested in. So the notch sensitivity is here, is the Q. And using my razor sharp eye, I estimate it to be 0.85. Question on using this chart. This is the notch sensitivity chart. Not done. Torsion. So this is the torsion chart for KT. Same usage. Now you tell me, what's the first step? In using this chart, what's the first step? Pick the line based on not R over D, D over D. Big D over small d, 1.5. I have this line D over D equals 2. This line D over D equals 1.33. So yeah, somewhere in between those two lines, right? Let's draw our magic art